Welcome, chemistry people. This is Mr. Beckman, and I have a white pen. That's not going to work. Mr. B talking to you. We have the practice exam for AP Chemistry, and we must talk about the practice exam. Hey, you have this copy in front of you, and so let's talk ourselves through this. Each of these, I'll do this somewhat quickly so I can save you some time. They want to rank these guys in order. Oh, there's lots of chemicals. Oh my gosh. The first thing I would do is I would identify each of them as a strong acid, a strong base, or a salt. Let's actually kind of walk ourselves through it. First of all, I would look at HCl, and I see HCl is a strong acid. So he will have a very low pH. The next thing I see on here is, I don't have a strong base on here. Okay, well, okay. But I do know that, for example, HCN is a weak acid, right? Ammonia is a weak base. And then HNO2 is a weak acid. Those are just those are the acids and the bases and such. Now, these other three chemicals, I'll underline, say, in blue here, sodium nitrite, sodium chloride, and ammonium chloride are all salts. Remember, salt is an ionic compound. Ionic compounds, they are the compounds that are metal, bonded to non-metal. So if I have sodium nitrite here, now the thing you need to realize is that the sodium is essentially irrelevant and unimportant. What we have essentially is we have the nitrite ion. Now nitrite is the anion of the weak acid HNO2, right? So we'll figure this out, you'll see. So if HNO2 is a weak acid, that makes NO2 negative to be a weak base. So we're going to have to kind of look at this weak base and compare it to ammonia, decide who is stronger. Now sodium and chloride are both part of the NaCl-nosos, therefore they are both irrelevant. So the pH of this is 7. I don't even think about this one. He'll be right in the middle of everybody in terms of our list. And my last one over here is ammonium chloride. Now the chloride, because he is part of the NaCl-noso, is irrelevant. So the ammonium is the key ingredient. Now ammonium's partner is NH3, which is a weak base. So his opposite, or his partner, his conjugate acid, makes him a weak acid. So we can kind of get our order started. I want to go from lowest pH to highest pH. The lowest pH would be the strongest acid. There's only one strong acid, so HCl is way right here. Okay, and right in the middle is going to be my salt, so I'll say NaCl. Now I've got several weak acids. Let's look at our weak acids. I've got HNO2 right here. I've got HNO2, and the other weak acid I happen to have is ammonium, NH4 positive. Now I don't know if these things should be flipped or not, but they're both in the weak acid category. In the weak base category, we have got the nitrite ion, and we have the ammonia. And so here is my list, and I can decide, I've decided which one is stronger or weaker. Now to do this, I'm going to need to use my tables in the back of the book. So I'm going to do HNO2 versus NH4. So I have HNO2, and I have ammonium. So the HNO2, I'm going to look up his Ka value. His Ka value is, I'm looking in the back of the textbook to find the value of nitrous acid. It is 4.0 times 10 to the minus 4th. Now when I look up ammonium in the back of the book, I need his Ka. But what I can find is the Kb of ammonia. And that's equal to 1.8 times 10 to the minus 5. Now I'm going to just guesstimate this K because the Ka times the Kb equals the Kw. Remember, Ka times Kb equals Kw, or the coefficients have to add up to the 14. The Ka of this weak acid is about going to be 10 to the minus 9th, because 10 to the minus 9th plus 10 to the minus 5 adds up to 10 to the minus 14th. So if I look at this right here, 10 to the minus 4th is a much bigger number than 10 to the minus 9th. So therefore the nitrous acid is a stronger acid than the ammonium. So did I do that right? Oh yes, so it's going to be HNO2 and then ammonium. So I did that right. I was just arbitrarily doing them though. Okay, now let's do the nitrite and the ammonium ion. Well, actually the nitrite, all right, let's get it. So you got a nitrite and ammonia. So I've got NO2 negative and I have ammonia. Now I'm going to do the base thing. The Kb of this, we just did that a minute ago, is 1.8 times 10 to the minus 5. Now I need to find the Kb of this. But I know that the Ka is about equal to 10 to the minus 4th, right? So therefore the Kb of nitrite will be about 10 to the minus 10th. That makes this the weaker of the two and makes this the stronger. Now, this is going to be a wheel. The stronger one, of course, is going to have a higher pH. So therefore, let's see if I got it right. Oh my gosh, I'm amazing. Nitrite and then ammonia. So the answer is this order right here. Kind of a long answer in that one. Okay, number 2. All right, this one's a lot easier. Which of the following acts as base? Remember, what does a sheep say? They say bad base acceptor, acid donor. That's the Bronsted-Lowry definition. What do they accept? They accept protons. So if you look carefully at this hydrogen, one of the hydrogen, the H3, comes and joins the water to make the hydronium ion. So the donor is an acid. The acceptor is a base. Bad. That makes this, of course, the substance that receives the hydrogen becomes the conjugate acid, and that makes this the conjugate base. So which are the acids and which are the bases? The acids I will circle in, say, blue. That is an acid, and that is an acid. And then the red will be the base. Should have switched that, I guess. Okay, you got that? That was a lot easier than number 1, wasn't it? Number 2, what's the equilibrium expression for HOCl? Now, HOCl is a weak acid because he's not one of our list of strong acids. I write the dissociation of his H positive plus OCl negative. The expression is simply writing that Ka equals concentration of hydrogen times concentration of OCl negative, hypochlorite, over the HOCl. It's a very simple problem. Products over reactants, ignore water because it is a liquid. Number 4, write the stepwise dissociation of the diprotic acid H2CO3. Remember, diprotic acids or triprotic acids break apart one step at a time. So you say H2CO3, it's a weak acid, double arrow, makes H positive plus HCO3 negative. And then we can say HCO3 negative breaks apart into H positive, and then the carbonate ion, CO3 2 minus. Kind of simple on these particular problems. All right, now why is sulfuric acid, H2SO4, stronger than sulfurous acid, H2SO3? Now you've probably memorized that sulfuric acid is a strong acid, but how do you know that it is, or why is it, the big why? The answer is, of course, you have an extra oxygen, and the more oxygens, the stronger the acid, because oxygen is a highly electronegative ion, or atom, pardon me, and therefore it draws the electrons closer to the sulfur, this side, which makes it more polar. So it is more polar, and more polar means stronger bonds, or makes stronger acid because it makes for weaker bonds. Okay, which is the conjugate base? All right, it's that whole movement of the electrons. It's similar to that last one. The acetic acid, the hydrogen moves over here, makes this. This is going to be the conjugate acid, and this is the conjugate base. That's a pretty easy question, isn't it? All right, number 7. Rank the following from strongest to weakest. I think actually they are in order. The strongest one has more oxygens, and the more oxygens, they're all ClO type. They're oxy acids. We would use the terms oxy acids of chlorine. So the strongest one has the most oxygens and the weakest has the least oxygens. They're actually in order here. I should have probably typed that in a different order, but that's okay, not a big deal. Okay, now these reaction quizzes, you got to write the net ionic equation and answer some questions, right? Solid calcium oxide CaO. Remember, you have to play the charge game. Ca is charged plus 2, oxide minus 2 from your periodic table. Reacts with water. Now you need to realize, very importantly, and very, very, very important, that if you have a metal oxide and you add it to water, it always makes a base. So if this of course, what is the base? The calcium's like, well, it simply makes calcium hydroxide. Now you have to do the OH2, and I believe that's balanced. So that's the net ionic equation. You know the ionics. Now what color does it turn phenolphthalein? Since it is a base, phenolphthalein in a base is what color? I'll even make the right color with the pink. It is a pink. In fact, I think this is right here. This picture is the pink phenolphthalein. Phenolphthalein, right? Okay, sorry. I get carried away sometimes. It's so exciting, the chemistry. It just makes my brain full. Okay. All right, what about sulfur dioxide? Again, we have a oxide, and it reacts with water. Well, this is a non-metal oxide. Sulfur is a non-metal from the periodic table. And this simply you just add them together, H2SO3. It's a weak acid, so I do not dissociate it. Now, what will it do with bromothionyl blue? Now, bromothionyl blue is blue in a base, blue base, However, in an acid, it is what color? It is red. So the answer to this one is red. Oh, I should use my red pen, red. All right, we like this, okay. Now, we're getting more complex here. Excess hydrochloric acid. Now, since it's hydrochloric acid, I'm going to write H positive plus Cl negative. I must dissociate it because it is a strong acid. And it's added to a solution of sodium phosphate. So sodium is in a positive. I must dissociate it again because it is a weak acid. Or it is a soluble compound, in Naconoso, plus phosphite. Phosphite is PO3 negative. Now we need to find somebody to get together. Well, the Na and the Col, don't get together. And it's an excess of hydrogen. It's going to make H3PO3R, phosphorus acid. pH acidic, basic, or neutral. Since you made an acid, I'm going to call this an acid. That's pretty easy, isn't it? All right, next question. Equal molar amounts. These are tough, these equal molar amounts of hydrogen, sodium, hydrogen carbonate. Sodium is Na positive. I dissociate it because of the Na, plus hydrogen carbonate. That's bicarbonate like I found in baking soda. In fact, sodium hydrogen carbonate is baking soda. Reacts with potassium hydroxide. I dissociate that again because of the because of the thing. Now don't forget, it's very, very important. Now Lee, you must always, you do this so many times, you must put on your charge. Without the charges, it's wrong. Lee, you watch that, or I'll get you, I'll hit your head and make you smart that way. Okay. Now, all right, when I take these and I put them together, the key thing is they're going to get together one at a time. So the hydrogen is going to react with the hydroxide. I think we talked about in class that hydrogens and hydroxides, they have a love affair. They love each other. It is like French men and women. And so, I don't know if I've just offended the world. Who cares? Okay. This, of course, makes HO2O or HOH plus carbonate. The potassium and the sodium cancel out. All right, now what we do next, calcium is added to hydrochloric acid. So calcium is Ca. It's just calcium, no charge on this because it is just elemental calcium, and it reacts with hydrochloric acid. Okay, so I'm going to split this apart. Now let me give you a little hint here on this particular question. When they ask you the secondary question, what would happen when a gas is given off, the presence of a flame? That's telling you a gas is given off. Now, what gas is given off? Now, this is actually a redox reaction. This is not an acid-base reaction. The calcium is going to go up in charge to calcium 2 positive. And the hydrogen is going to go down to hydrogen gas. The chloride actually doesn't play a part at all. And you just need to put a 2 here. Now, when you produce hydrogen gas, what happens when you put hydrogen gas in the presence of a flame? Well, the answer is, of course, it will explode, catch on fire, make a popping noise, something along those lines. You know, I think on the last question, I'm wondering if I forgot to answer the question, ooh, will the pH be acidic, basic, or neutral? I don't know. I think it's going to be basic. So we're adding hydroxide to something here. This is a base. We're adding more base. Yeah, this is a base. Or basic. Okay? All right, now we get the calculators out. Now we're going to do some mathematics. All right, the first question says, what's the pH of a 0.25 molar solution of hydrochloric acid? What do you know about hydrochloric acid? You know, right? Aaron, you are correct. Hydrochloric acid is a strong acid. So guess what? When strong acids break apart, they break apart completely. They're like a high school romance. What's true about all high school romances? They always break up. Every one of them. 100%. I know that's not good news for you people who have boyfriends and girlfriends, but it is true. So what is that concentration of the hydrogen? You don't even need to do an ice table. It is 0.25 molar. So you take the negative log of 0.25, and that's, my friends, is the answer. So I take my calculator. Probably should turn it on. Take the log of 0.25, and you get 6, or 0.602. Now, sig fig wise, let's talk that. Remember, pH is sig figs. I should probably say 0.60. I'll keep 2 significant digits, and they only count the digits past the decimal. Okay, so that was that question. Question 9. Question 10, the percent dissociation of a 0.45 solution of ammonia. Now the key. It is the key. It is always the key. Now, Caitlin, you know this is true. What is the key? You must always write the correct equation. Without the correct equation, you will be wrong and be very unhappy. We must not have unhappy students. All right, so ammonia, when in doubt, what do? You react with, that's right, you react with water. So I'm going to write water as HOH though, double arrow, and that's going to make ammonium. Again, remember, what's the rule? Partners must always appear on opposite sides, plus hydroxide. Now we have, do a nice table, ICE. So this is 0.45, this is 0, and this is 0, minus X, plus X, plus X, and then we'll get 0.45 minus X, X, and X. So I can say that the KB is equal to, new screen, KB is equal to the concentration of the ammonium. Don't forget the charge. Lee, did you forget the charge? I know you forgot the charge. Times the hydroxide over the ammonia. Well, we know this to be 1.8 times 10 to the minus 5 would be equal to x squared over, I should probably remember this, but I forgot the paper, 45. 0.45 minus x. I now use my fun solver. I take the math as 0 onto my calculator, and I must do the solver clear. So I type in, I'm going to type this formula here and do times, and then that's not an x but times, and then I'm going to subtract the x squared. So I type in 1.8 e negative 5 parentheses 0.45 minus x parentheses minus x squared equals, choose a nice small number, alpha solve, and I get x is 0.0028, okay? And that's equal to the concentration of the hydroxide. It did ask for the percent dissociation. Yeah, percent dissociation. Remember, percent dissociation is just x over initial times 100. So 0.0028 divided by 0.45 times 100. So on my calculator, actually, it remembers that x is 0.028. So I'll take x divided by 0.45 times 100 gives me 0.63%. All right, that wasn't terribly difficult, was it now? All right, question number 11. What is the pH of a solution of HOCl? And I have the Ka here, so that'll be great. So I'll say, I got to write the equation, right? Caitlin, you must write what? The equation, that's right. HOCl dissociates into H's and OCl negatives. This is 0.25. And 0 and 0. I must write the ice. I love ice. Ice is good for you. Minus x. 0.25 minus x plus x and x plus x and x. So that I can say 3.5 times 10 to the minus 8 is equal to x squared over 0.25 minus x. Again, I'm going to plug this into my solver. Math 0, arrow up, clear out the last bugger. 3.5 e negative 8 times 0.25 minus x, parentheses around that 0.25, minus x squared, messed up, x squared, and do the old alpha solve thing, and I get x to be, now this is an interesting thing, I get x equals 9.35. Now, I've got an arrow over on my solver, on my TI calculator, and it's actually times 10 to the minus 5. And this x, I like you to write this, equals the concentration of the hydrogen. Because they asked for the pH, and so then now I quit and I do the negative log of x. And I get 4.029. Now sig figs, I got 2 here and 2 here, so I'm going to say 4.03. So the pH equals 4.03. Take the negative log of that number to get that answer. I'm not showing that, but I think you can figure that out. Now here is the uber long question, and it will be on the test. I promise the test is, oh yes. Okay, it's the Ka of a polyprotic acid and all that kind of stuff. We have the weak acid, oxalic acid, and we have 2 values, and we have to do this one step at a time. So it's H2C2O4. I'm going to do one step at a time. H2C2O4, and he dissociates into hydrogens, and then HC2O4 negative. and I must do an ice table. Now my initial concentrations was 0.35, so this is 0.35. That's 0 and 0 minus x, 0.35 minus x, plus x, plus x, x, and x. So now I know my Ka1, which is 6.5 times 10 to the minus 2. So I can say 6.5 times 10 to the minus 2 is equal to x squared over 0.35 minus x. And then I do the solver thing, and I get x equal to, I don't know, the KISS solver. So math 0, clear it out. So 6.5, second function e, negative 2, parentheses, 0.35 minus x, parentheses, minus x squared, enter. Do the alpha solve thing. I get x to be 0. Pretty big number, 12 molar. Okay, now that's the concentration of the hydrogen here and the HC2O4 negative. Did you forget the charge again, Lee? No forgetting the charges. All right, so you've got that, and that helps us. That's going to help us with a number of things. And then I'm going to take the HC2O4 negative and dissociate that into hydrogens plus the C2O4 to negative. Now, the initial concentration of the HC2O4 was from the previous problem, which we call as 0.12. This is 0, but the hydrogen is also 0.12. So minus, let's call it y, plus y, plus y. So 0.12 minus y, no, 0.12 plus y, I forgot that, and y. Now I'm going to use the Ka2, and the Ka2 is 6.1 times 10 to the minus 5. And that's going to be products over reactants, or 0.12 plus y times y over 0.12 minus y. Now in my calculator, I'm going to say 6.1 e negative 5 times 0.12 minus y, actually x, I'll type in x in this case because the x is going to work better on the calculator, minus this whole term, 0.12 plus x times x. That's how I'm going to set it up, because I have to set it equal to 0. So let me get back to my solver here. I'm there. So I'm going to say 6.1, second function e, was it negative 5, parentheses, 0.12 plus, is this a plus? No, 0.12 minus x, parentheses, minus parentheses, 0.12 plus x, parentheses, parentheses, x, parentheses. How's that for a lot of parentheses? And this is a very small number, and I think I'm going to get 6.1. That's what I thought. Y equals 6.1 times 10 to the minus 5. You say, huh? How'd that work out? Well, it turns out, by the way, that the y here is a very small number here. So if you take 0.12 plus y and 0.12 minus y, if y is really itty-bitty, then it becomes, the 0.12's essentially cancel, and then the Ka2 is equal to y. Now, what are the answers to these problems? Now let's think this through. We have a number of different chemicals we need to test. We've got H2C2O4, the oxalic acid. If you recall that, we found that to be 0.35 minus x. Okay, and x, if you recall, was 0.12, right? So 0.35 minus 0.12 is 0.23. All right, and the concentration of the HC2O4 negative, I should see brackets. Notice I put the charge on there, Lee, of course, is just equal to x. It's actually x minus y, but y is really small, so that's going to be 0.12. The concentration of the C2O4 2 negative is equal to y, which was 6.1 times 10 to the minus 5th. By the way, all of these would have units of molarity. And then the last chemical is the hydrogen. The hydrogen is actually equal to x plus y, but since y is very tiny, it's 0.12 molar. And if you're asking to find what is the pH, I think it asked that. pH is the negative log of the hydrogen, so you take the negative log of 0.12, which would be a very low pH, 0.92. All right? That's the longest question on the test, I can promise. All right, what is the pH of a 0.43 mole solution of ammonium chloride? Now, ammonium chloride is a salt, an ionic compound that has the metal and the nonmetal. Now, this is actually not a metal and nonmetal because ammonium is like N and H are both nonmetals. But you consider ammonium kind of like a metal, so this is still considered a salt. Who do I get to ignore? Well, it's that chloride. The chloride does not matter. So I'm going to write NH4 positive, and you can actually just dissociate it into ammonias, remember the partner deal, plus hydrogens. Now, I do not know the Ka of this. This is an acid, so I can do an ice problem. You'll see. So this will be 0.43, 0 and 0, minus x, 0.43 minus x, plus x, x, plus x, x. So the Ka, though, will be equal to x squared over 0.43 minus x. Of course, the trick on this problem is that I did not give you the Ka, but the Kb. But you know that the Ka times the Kb is equal to the Kw. Kw is the K of water, which is 1 times 10 to the minus 14th. So I can just take, and I know this, the Kb, 1.8, so you divide both sides by 1.8. So I take 1.0, 1e negative 14 divided by, what is it, 1.8 e negative 5, right? Yep. And I get 5.6 times 10 to the negative 10th. So now I go back to the solver guy, and I clear it and clear. All right, so 5.6 e negative 10 times 0.43 minus x, parentheses, minus x squared, period, alpha point, very small number, alpha solve, and I get 1.55. I get x to be 1.55 times 10, arrow over to the minus 5. And they're asking for the pH, and since this is the hydrogen concentration, I'll take the negative log of x, and I get 4.81. pH equals 4.81. Okay? Next question, 14, almost there. The pH of a weak monoprotic acid is 3.38. What, with an initial concentration of 0.015, what is the Ka of the acid? Now, I've just said HA, so if I've got HA, it's going to dissociate into H's and A negatives. All right, got to know these are reactions, I, C, E. Now I know my initial concentration to be 0.0150, 0.0150. This number is 0, and this number is 0. And of course you'd say, well, minus x, 0.0150 minus x, plus x, x, plus x, x. But wait, it's asking to find the Ka. Usually we know the Ka, we solve for x. Oh, but wait, let's go back and reread the question. I said the pH was 3.38. Well, what do you know about pH? Well, 10 to the negative pH is equal to the concentration of the hydrogen, right? So if I take 10 to negative 3.38, forgot that number there, 3.38, so I'll take my calculator, 10 to the power of negative 3.38, that is the hydrogen concentration, which is 4.2 times 10 to the minus 4th. But what's that actually equal to from an algebraic perspective here? That's right, it's x! X, x, x marks the spot. If that's x, and you know x, we can do this because we know that if we take, you know, the Ka expression, which is the hydrogen concentration, times the A negative, whatever A might be, over HA, and we plug these in, we can solve for Ka. And that's what each of these terms are. So this is going to be equal to 4.2 times 10 to the minus 4th, and essentially it's x squared, so you square that, divided by 0.0150 minus the 4.2 number, 4.2 times 10 to the minus 4th. So I'm going to just type that into my calculator. So 4.2 double E negative, what is it, 4 squared divided by parentheses 0.015 minus 4.2 double E -4, close parentheses, and I get a Ka equal to, I need more space, I'll scrunch it on the bottom, 1.2 times 10 to the -5. Okay? Now that, my friends, is your practice exam. You have exam next time. You must study. Lee, you must study. No. All right. Now you can't study with Caitlin because sometimes that creates problems. Okay. But we won't get there. All right. Have a great day. You must smile and be a happy kid because we have much to learn in AP Chemistry Land because chemistry is fun. Bye.